Welcome back to the deep dive. If you feel like the AI frontier is moving a little too fast to track, you're definitely in the right place.
Yeah, it's a lot.
Today we did something, well, something a bit unique. We took a rapid snapshot of a whole bunch of research papers, all submitted on the exact same day, 2026-0108.
The idea was to give you a real-time, completely unfiltered look at the bleeding edge of large language model development.
And what a look it is.
It's a remarkable flow of innovation, really. It covers everything from, the basic economics of computation all the way to the deepest, most abstract realms of theoretical physics.
So our mission today is to synthesize this huge stack of sources and give you, the listener, the key takeaways.
Right. We're going to focus on three core tensions that I think really define the future of AI engineering. First, how do you make these huge models cheap and efficient at scale?
Okay, efficiency.
Then, how do you get granular, precise control over their output? And finally, this is the big one. How do you fundamentally prove they're reliable, that they're stable, both conceptually and mathematically?
Exactly. We're looking at the foundational work that's trying to solve those very problems. So if you want to understand where the next generation of LLMs is going, this is your shortcut. Let's just jump right in with that first challenge. The efficiency wars.
I mean, the single biggest headwind facing large-scale AI is simply the cost.
The raw cost, yeah.
We're talking about the expense of training and then running these massive models, which, it just continues to skyrocket right alongside their capabilities.
And that cost curve starts right at the very beginning, at the pre-training stage. You can optimize the hardware all you want, but if your core algorithm isn't right, you're just burning money.
Precisely. And one of the most critical variables there in large-scale pre-training is optimizing the learning rate, or LR, and finding the right LR configuration. Well, researchers have basically called it a formidable challenge because you're fighting this razor-thin trade-off between the money you spend and the performance you get back.
So if the learning rate is too aggressive, the model training just collapses.
Yep.
But if it's too slow, you've essentially wasted millions of dollars on compute time for, diminishing returns. It's a Goldilocks problem on a terrifying scale.
It really is. The breakthrough documented in these sources comes from what's called the fitting paradigm research. They introduced a new scaling law specifically for the search factor used to find that optimal LR.
Okay, so let's try to unpack this for the listener who may not speak mathematical notation. The old process, the one for optimizing the search complexity, was what, dollars?
That's right.
This new scaling law drastically reduces that to a near linear function, a dollar CDC. So in practical terms, how big of a shift are we actually talking about here for a large org trying to train 100 trillion parameter model?
Oh, it's transformative.
Yeah.
I mean, in simple terms, moving from a cube complexity to something near linear. It means what might have taken a week of really expensive searching can now be predicted and executed in just a matter of hours. And with far greater precision. This is a massive operational win. It fundamentally changes the economics of training the next generation of foundational models.
And then what's so interesting is that this new research, it directly challenges the scalability of a really widely adopted method called mu transfer.
It does.
So it suggests that even the bedrock best practices we thought were stable are, being overthrown in this constant pursuit of hyperscale efficiency.
That's it. The frontier is never settled. And moving beyond just training, the next big focus is on something called collaborative inference.
Okay.
So making expensive big models, LLMs, work seamlessly and cheaply with small language models, or SLMs. The dilemma is classic. LLMs are brilliant but costly. SLMs are fast and efficient, but they just lack that generalization power of their larger cousins.
So the solution is to get them to talk to each other, but not just pass a job off. They need to collaborate at the token level. Which is where this thing called FusionRoute comes in.
FusionRoute is a token-level multi-LLM framework. It uses a really lightweight router that does two things at the same time. First, it selects the best expert model for that specific decoding step.
Okay, so it picks the specialist.
Right. And second, it contributes what's called a complementary logit to that expert's output.
A logit, just for our audience, is basically the model's unnormalized prediction score. It's raw confidence in what the next word should be.
Exactly.
So the router isn't just selecting the expert, it's adding a tiny corrective nudge, a complementary piece of confidence, to refine the choice right then and there.
And that complementary piece is really key. It's theoretically grounded. Researchers show that if you rely only on the fixed, unnudged output from the expert, you're fundamentally limited. You need that extra little refinement from the router to get back to the optimal prediction.
That's really clever engineering. But the truly breathtaking cost reduction comes from a method called RelayLLM. This seems to shift the control dynamic completely.
It really does. Here, the small language model acts as the active controller of the whole generation process.
How so?
Well, it's highly efficient because the SLM just handles the vast majority of the text generation itself. It only dynamically calls on the expensive large language model for what it decides are critical tokens. It uses a special internal relaying command to do that.
The 1.07% invocation figure is just astounding. To get high accuracy while only calling the LLM for barely 1% of the tokens, I mean, that suggests they must have a nearly flawless way of identifying what a critical token even is. What happens if the small model misses a genuinely pivotal token and just, relays jump? Doesn't the whole thing fall apart?
That is the core challenge they solve. The SLM is trained to identify when its own internal uncertainty crosses a certain threshold. It's like a sort of metacognition.
It knows what it doesn't know.
Exactly. And they showed this threshold method is highly reliable. By only calling the LLM that tiny fraction of the time, they got a 98.2% cost reduction compared to other, less sophisticated routing methods. That's a huge architectural shift.
So moving from general text to more specialized thinking, we have something called GlimpRouter, which is all about large reasoning models. This is where I thought the surprise insight was.
The aha moment.
Yeah. The idea that the difficulty of a complex reasoning step can be inferred from its very first token.
This is the aha moment phenomenon translated into a routing strategy.
Mm-hmm.
They found that the entropy, the uncertainty or randomness of that initial token is a really strong predictor of how difficult the rest of the thinking process is going to be.
So high entropy on token 1 suggests the model is confused and it needs to phone a friend.
Pretty much, yeah. So GlimpRouter uses that entropy threshold, which is totally training free, by the way, to decide if the lightweight model can handle the whole reasoning chain or if it needs to immediately route the step to a heavier, more capable model.
And it works.
Oh, yeah. All driven by just a glimpse into the model's thought process. This resulted in a 25.9% latency reduction and a 10.7% boost in accuracy on really demanding reasoning tasks. It's a great demonstration that efficiency isn't just resource allocation, it's about predictive inference, driven by, like you said, model psychology.
Incredible. So, okay, we've nailed the engineering challenge of making them cheaper and faster, but speed and cost, they don't matter if the output is unreliable or uncontrollable.
Right.
Which brings us neatly to part 2, moving from maximizing efficiency to ensuring perfect control and trustworthiness.
And that is where we shift from, scaling architectures to really governing output behavior. Real-world LLM deployment isn't about getting one simple thing right. It's about satisfying multiple, sometimes contradictory objectives all at once. Researchers are calling this compositional steering.
And the method to achieve this compositionality involves something called steering tokens. So they're embedding individual natural language instructions like be helpful and be brief into their own dedicated tokens.
And the novelty here is critical. Most prior work tried to steer the model by intervening in its internal thought process, its hidden activation space.
Right, messing with the guts of it.
Exactly. But these new behavior steers, they live directly in the input token space, right alongside the prompt itself. And this makes the zero-shot composition just vastly more effective.
So by treating the behavior steer as just another input token, the model can process instructions like, be extremely friendly, highly professional, and slightly sarcastic all at once, even if it has never seen that exact combination before.
Precisely. They specifically train a dedicated composition token that acts as a kind of blending agent. It generalizes exceptionally well to unseen compositions, including ones with a totally new number of behaviors it needs to satisfy. It's truly modular control.
So that handles the steering.
Yeah.
But protecting the integrity of the output, that's a whole separate challenge.
Yeah.
Let's talk about watermarking, which is so crucial for tracing AI-generated content. If you apply a traditional token-based watermark to a model that's generating, say, a complex logical proof or reasoning LLM, you risk corrupting the actual logic.
This is the exact problem that ReasonMark solves. It wisely decouples the generation process into an undisturbed thinking phase, and then that's followed by a watermarked answering phase.
So the watermark doesn't interfere with the logic creation.
Right.
But how does it manage to apply a detectable watermark without introducing noise that breaks the math or the logic?
It uses a concept called a criticality score. The score identifies the semantically pivotal tokens, the core logical stepping stones from that thinking trace.
Okay.
These are then distilled into what's called a principal semantic vector, or PSV. The PSV acts like a semantic map that then guides the watermark's strength, making sure the mark is detectable but adaptively weak on those high criticality steps.
And the results speak for themselves. They reduced text perplexity, so the text felt more natural, by 0.35 points, and actually increased mathematical accuracy by 0.67 points, all while proving the watermark was robust.
It's a huge step forward for accountability. And, another approach focused on semantic quality is something called SemPA, which works to improve sentence representations or embeddings within the LLM.
This often proves difficult, right? Because boosting that representation quality usually sacrifices the model's main function, its ability to generate new text. What strategy did SemPA use to get around that?
They used sentence-level direct preference optimization, or DPO, but they applied it specifically to a paraphrase generation task.
Oh, okay.
By doing this, they effectively aligned the model's internal semantic preferences, making sure similar sentences have similar embeddings without having to change the fundamental architecture.
So it learns what similar means by optimizing for what it prefers in a paraphrase, ensuring the semantic space is tightly organized while keeping the generative function totally intact.
And they provided the theoretical backbone for it. They proved this preference alignment is mathematically connected to standard contrastive learning under a pretty sophisticated framework called placket-loose. It means they're getting better, more robust, and theoretically sound semantic representations.
Okay, so we've made them cheap, fast, and controllable. Now for the final, most abstract, but I'd argue the most important challenge, the deep foundation.
Right.
How do we reliably evaluate these advanced systems, and how do we ensure they don't just fundamentally break down on a logical level? And we start with the paradox of LLM judges.
LLM as a judge systems were, they were introduced as the solution to scalable objective evaluation. Instead of using expensive, slow humans, you just ask a powerful model like GPT-4 to score the output of another model.
Seems like a good idea.
It did. But recent findings revealed an opposite. A profound reliability paradox.
What exactly is the paradox?
The judges are highly consistent with themselves. So if Judge A gives a score of 8, they will consistently give that 8 if they see the same output again. But they exhibit near zero interjudge agreement.
Near zero. You mentioned Krippendorf's alpha was measured at what, 0.042?
Yeah.
For the listener, that's the gold standard for reliable comparison. A score that low is functionally zero agreement. It suggests that, comparatively, these judges are almost useless as interchangeable measurement instruments.
They're not random, but they are highly subjective. This disagreement, though, it's structured. Researchers found these judges have evaluative fingerprints.
Fingerprints?
Yes. A classifier could identify which specific judge produced an evaluation with 77.1% accuracy just from the rubric scores alone.
Wow.
And if you look within model families, say, distinguishing an evaluation from GPT 4.1 versus one from GPT 5.2, the accuracy shot up to 99.6%.
That's fascinating. It means each judge isn't measuring some shared objective truth of quality. Rather, they are implementing their own distinct, stable theory of quality, their own evaluative disposition.
Precisely. So averaging their scores doesn't get you closer to the truth. It just creates this synthetic verdict that doesn't actually align with what any single judge values. And this limitation is already driving the necessary transition to what's being called agent as a judge.
Agentic judges, that sounds like they're designed to solve that structural subjectivity and, frankly, the shallow reasoning that the LLM judges failed on.
They are. Agentic judges use much more robust multi-step techniques. We're talking about explicit planning, tool-augmented verification.
So they can use search engines and things to check facts.
Exactly. They also use multi-agent collaboration and persistent memory. This shifts evaluation from a single, subjective, potentially biased pass to a verifiable, nuanced, and structured process.
Okay, that handles evaluation. Finally, let's go to the bedrock. This is the abstract, highly foundational work trying to fix the core problem of hallucinations.
Right, those logical inconsistencies you get from semantic noise. This is where AI research genuinely meets theoretical physics.
It really is.
This research suggests that current architectures, like your standard transformers, they operate in this vulnerable area they call the metric phase. And in this phase, the causal order and the logic sequence are susceptible to symmetry breaking, which causes what they call gapeless decay in fidelity.
So if I understand the analogy, if current models are like a rope that easily frays under semantic stress, they aren't fundamentally stable when they try to reason over really long sequences.
That's a good way to put it.
So what's the fix, theoretically?
The fix is to identify robust inference as something that should inhabit a symmetry-protected topological phase, a concept borrowed directly from condensed matter physics. In this robust phase, logical operations are formally isomorphic to non-abelian Enneadian braiding.
Okay, non-abelian Ennean braiding. That is profoundly theoretical. Let's bring that back down to earth for a moment. Is this concept essentially about, like, braiding the logical steps so tightly and in such a specific geometric way that a cut or some noise on one logical strand doesn't unravel the entire system?
That is an excellent way to simplify it, yes. It means the logical integrity is protected by a topological invariant, the shape of the logic itself, making it immune to local noise below a certain critical threshold.
So what does this translate to in an actual AI model?
It results in a new architecture, the Holonomic Network. This network maintains invariant fidelity below that noise threshold by revealing a macroscopic mass gap in the logical space. But the most powerful empirical result is what they termed holonomic generalization.
Tell me about the generalization.
The topological model maintained perfect fidelity, perfect logical correctness, when extrapolating 100 times beyond the length it was trained on.
100 times.
Yep. For example, training on sequences of 50 tokens, and then maintaining absolute accuracy when reasoning over sequences of 5,000 tokens.
Perfect fidelity at 100 times the training length. That isn't incremental. That proves a new universality class for logical reasoning, linking stability not just to the volume of data, but to the fundamental topology of the semantic space itself.
It is a profound finding, tying the deepest physics concepts to the core engineering challenge of reliability.
What really stands out to me is how cohesive and interconnected all these developments are. This research, it isn't just a list of random papers, it's a simultaneous push. The search for a cheaper learning rate feeds the ability to train bigger models, which then require more reliable agentic judges.
Which ultimately need that fundamental topological stability to prevent hallucinations in the first place.
Exactly. You, the listener, are witnessing a field that is maturing from a prediction engine into an engineering science, one defined by hyper-efficiency and hyper-reliability.
The sheer pace and depth of the foundational changes happening on a single day like the one we just examined is just genuinely breathtaking.
So we'll leave you with one final thought, building on those evaluative fingerprints of the LLM judges. If researchers can show that every judge, every model has its own distinct, stable theory of quality, does a universal objective definition of LLM quality even exist? Or must we accept that all evaluation is inherently subjective, filtered through the specific stable disposition of the judge doing the assessment, something to chew on as you go about your day?